Hi, I plan to make a few videos about the phenomenon named as a skin effect. Now in this first video I will just describe the phenomena and also I will show you the consequences of a skin effect, and at the end I will show you how to perform a simple simulation in COMSOL multiphysics and how to analyze a skin effect and calculate AC resistance because of the skin effect. In the next video I will explain the physical phenomena that causes a skin effect, and we will solve Maxwell's equation to obtain the formula for current density um, due to the skin effect in a round wire. Okay, so let us assume that we have a wire. In this case it's a round wire and the current I is passing through this wire. Now we look at the cross section of this wire. Obviously it would be a circle, so we have a circle here. Um, Imagine if we have a current that doesn't change with time. For example, in this case, we have a DC current that doesn't change with time. Now, if this current passes through this wire, it happens that this current would uniformly distribute across the cross section of this conductor. Okay, so this is case number one. Now, imagine if we have a current that changes with time. So, for example, I took a sinusoidal current. I is IP times sine omega t. Now, if this current passes through the same conductor, what we observe is that the current tends to flow near to the edge of the conductor. And basically, more current flows in this region compared to the center part. Now, in the third scenario, if we take a current that has even higher frequency, so in this case a sine wave with higher frequency, we observe that most of the current will actually flow near to the edge of this conductor, and actually the inner part of the conductor will not be used to transmit current. Now this phenomena is named as a skin effect, which basically whenever we have a time varying current, um, the current tends to flow near to the edge of the conductor. As I mentioned, the reason why this happens, I will cover it in detail in the next video. So now let us look at the consequences of skin effect. So in order to see the consequences, we have to look at the resistance of a wire. So in case of this wire, for example, we know that the resistance is basically rho multiply L divided by cross section. So L is the length, cross section A is cross section, and rho is a specific resistance. Now assume that we have a fixed material here, the wire is fixed, so rho will be fixed, and L, the length of this wire where we apply the voltage such that the current will flow, that L is also constant. Now A, the cross section of conductor is constant, but how we use this cross section is not constant. Like in the case of DC, we use all cross section of conductor effectively. So basically the cross section that we have to put here is the real cross section of the conductor. However, in the case that we have a bit higher frequency, like in the middle case, the effective area that we use is not the actual cross section of conductor. It's less than the actual cross section of conductor. And if we increase the frequency even further, the effective area that we use to transmit current is even smaller. Now, if we put these areas into the formula of resistance, what we get is that the resistance in this higher frequency case will be the highest, and then in the middle case will be in the middle, and then for DC will be the lowest. So basically the AC resistance, it's higher than the DC resistance. And as the frequency increases, the AC resistance increases. Now, obviously, this has a negative consequence because assuming that we pass same amount of current through this wire, so when the resistance of wire is more losses will be produced inside wire, and that is not desired. Now, practical examples are, for example, generator stator bar. Well, power generator, they can carry huge currents like tens of kiloamps, and so we need to select a very large cross-section conductor. Now if we select a solid copper conductor like this, according to the skin effect, the current will flow near to the edge and the center part is not properly used. Now in order to solve this issue or reduce the effect of a skin effect, what we do is basically we create many smaller conductor inside, and we put some insulation in between such that they are not in touch. Now we will show in the next video that the depth in which most of the current flow through the conductor, this depth, we call it the skin depth, this depth depends on frequency and depend on material properties. Now, assuming that we use same material here and in these two cases, so copper has the same properties in both cases and frequency is also the same, so this skin depth will be the same. So obviously, if we divide it into smaller pieces, now most of the area of these smaller pieces um, will be used to transmit current because the skin depth is fixed in both of cases. In this case, the middle part is not used properly, but in this case, a lot of area, almost all area of each section is used properly. So in total, basically, we use the cross section more effectively than in the original case. So that is the practice that is done in reality in order to reduce the skin effect and reduce the RAC. Same case is also there for power transformers. In the low voltage winding, usually we have huge amount of current, so the cross section of copper has to be large. But of course, again, we do not select a very large copper conductor. Instead, they divide it into multiple conductors, and these conductors are in parallel. Obviously, each of them they have some paper around it to avoid direct contact in all locations, but at the end they are basically parallel, so they are connected together. And by this way, basically, we reduce the skin effect phenomena, and we use the conductor cross section more effectively. Now, this is a negative impact. There are many more examples that we can mention. In some cases, actually, skin effect maybe is useful. For example, when lightning strike an overhead line, waves will propagate. One of them goes to the right side, to the left side. Now, the lightning waves are usually very sharp. So like the front time is very small in microsecond range, and the tail is maybe hundreds of microsecond. Now, in the laboratory, to represent lightning impulse, we have some standard waveform. It's 1.2 microsecond rise time and 50 microsecond time to half magnitude for the tail. So it is obvious that this wave contains higher frequency and also medium frequency content. So now as the wave propagates along the line, those higher frequency components, they feel more resistance in front of them because the skin effect is higher at higher frequencies. So the AC resistance is higher for higher frequency. So the high frequency component of this wave basically feel more resistance, and that means that those components will damp earlier than the lower frequency. So as the wave propagate along the line, basically the high frequency component will be lost. So the sharp rise time of the waveform becomes smoother, and also some of the total components will be a bit of that will be lost. So the total magnitude of the waveform will also decrease a bit. So this is actually beneficial for us because when this waveform comes to the substation, obviously the damage that a sharp waveform with a higher magnitude can cause to the substation is more than the damage that a waveform with a smaller rise time and lower magnitude can cause. So in this case, we see that the skin effect actually plays positively. Okay, so now it's enough for the consequences. Let us look at how can we simulate this phenomena in COMSOL multiphysics. So again, in this case, we consider a round wire because we know that in z direction there is no change, so everywhere is the same. So actually we can reduce this model into a 2D model. So we only draw the cross section of the conductor in COMSOL, and the radius we assume is 1 millimeter, material is copper, and the current that is passed through this conductor we assume it is 1 amp. We are going to study this case for 3 scenarios. In the first case we have DC 0 Hertz. In the second case we have 5 kilohertz, and in the third case we have 500 kilohertz. And we will calculate the resistance in all of these cases. Compare the DC resistance with the AC resistance at 5 kilohertz and 500 kilohertz. Okay, now let us open COMSOL and see how to do this simulation. Okay, so I open COMSOL, make a new model, select 2D, and from AC/DC I can select magnetic field or magnetic and electric field. I select magnetic field here for this analysis. Study, select frequency domain, done. So from dimension, I select millimeter, and then right click, create a circle, radius 1 millimeter, so we can build it right away. Material, I right click and I click a blank material, permeability 1, epsilon 1, sigma is 5.86 e power 7 for copper. And in the magnetic field, I right click, create a coil, and select this coil. This wire will be the coil, and the current through the coil is 1 amp. And for the mesh, I select extra fine mesh. And also, since the skin effect basically happens at high frequency, it happens very close, very nearby the edge of the conductor. So I want to put some boundary layers here. It helps to have better resolution at that region. So I add a boundary layer, and then I click on this one, and I select all the boundaries. So you can select one by one, or you can click on here and select all of them. And so now 8th level, we actually built this. So now you can see that near to the edges, we have multiple meshes, which basically help us to better resolve the current density at that region. All right, so in the first case, I'm going to study for 0 Hertz. So DC. So we run the simulation. Okay, so this is the magnetic field distribution. I just right click on the result, create another 2D plot, right click, surface plot, and here I'm gonna select the current density, current and charges. So current density, I'm not gonna select norm of current, I'm gonna select the Z direction of the current. So as we can see, the current distribution is uniform, everywhere is the same. And if I click on somewhere on this, we can see that current is 3.18. Maybe I can change this one to ampere per square millimeter instead of square meter. So we can see that current density is 0.3183 ampere per square millimeter. Okay, so this is understandable. I will do some simple calculation right now, but first let me create a 2D cut line. So I also want to plot the current density across this cut line. So I have already created it in dataset. Now I create a 1D plot, right click, 1D plot, and again right click, line graph, and then from parent we select the cut line that we have built, and also here we again select the current density in Z direction. Of course, again the current will be equal everywhere. Because the frequency is 0, so current density will be uniform. But now let us do some simple calculation to see whether this number that we get is the actual number that we should get. So for the case of frequency is 0, we expect that the current is uniformly distributed, and so current density in this case, what would be the current density? J is basically equal to I divided by A. So the total current divided by area, which is 1 amp divided by pi R2. Okay, so I got rid of the pen attention because it distracted me. Okay, so this is 1 amp over pi R2, and then I can write R as millimeter, so it would be 1 over pi, and R is 1, then ampere per square millimeter. So pi is, so J will be basically 1 over 3 0.1416 ampere per square millimeter, not cube, which is equal to that number, I assume. 1 divided by 3.1416, this gives us 0.3183. So we got the same answer here. Okay, so now let us see how to calculate the resistance of this wire. What we can do is that we can actually right click on derived values and select the global evaluation, and here we click on expression and then magnetic field, coil parameter, and then we can select AC resistance. So if we evaluate this one, so we see that AC resistance, in this case frequency is 0. AC resistance is actually this much, 0.00054319. Okay. Of course, in this case, we could also calculate the resistance because it's a DC situation. So RDC is actually equal to L divided by sigma A. So L, this one is basically ohm per meter. So this resistance is ohm per meter. So L is 1 meter in this case we consider. So sigma is 5.86 multiplied 10 power 7. And then A is multiply 1 times 10 power minus 6 because it's 1 millimeter. Millimeter power 2 is 10 power minus 6. So RDC will be, so this one with that disappears, this one with this disappears, so we have a 10 here. So 1, okay, sorry, here we have also a pi here. So pi multiply 10 power minus 6, which is 1 actually, 10 power minus, or maybe I erase this one. It's pi times 1 times 10 power minus 6, and then we can now get rid of this, so that will be 10. So it's 5.86 times pi times 10, which will be equal to, if I do the calculation here, 1 divided by 5.86 divided by pi is equal this much, and another 10, another 0 will come there. So basically we have 0.05 and then 4, 3, 1. Okay, I missed another 10 because there is also another 10 here. 0, 5, 4, and then 3. So that is basically what we have here, 0.5431, which is actually ohm per meter. So we can see that the resistance that we calculate is exactly the resistance that we get from COMSOL. So the analytical value is the same. Now here COMSOL does this calculation for us to calculate AC resistance directly, but I want to be able to calculate the resistance with knowledge about the current density. So let us have some understanding here. So power, if we look at the power loss through a conductor, then let's say we have this conductor here. So now I'm going to basically write a little bit. So here I have a conductor, and then let's say this is L, this is A, the cross section, and we apply a voltage across this. The power will be basically V times I, and in case of the AC would be 1 over 2 V times I. But that one, or maybe I just keep this 1 over 2 if we assume that it's AC. All right, so then this voltage is basically applied, let's say here. So here we have the voltage. Let's say over this we have the voltage V. Let me move this one a bit down. This is not a good sign for the voltage. Maybe I should show it in a better way. So for example, I have a voltage like this here connected to this. Obviously electric field, so we can actually simplify this. So voltage E is equal V divided by D. So V is equal E times D. So E times, in this case, L. Maybe I should write here L also, not to confuse people. And then the current itself is I, it's like J is equal I divided by A, which means I is equal J times A. So this one will be multiplied by J times A. And then that one is equal 1 over 2 E times J, multiply the volume. So this is the volume of this area, because this volume of this cylinder, so the length multiplied to the area. We have length area here. And now I can calculate actually power density. So dP to dV is equal to 1 over 2 EJ. And E itself, we know that is equal to J is equal to sigma E. So what I can conclude is that E is equal to J over sigma. So the power density actually will be 1 over 2. If I replace E with J over sigma, it's J2 over sigma. And so now as the consequence, what I can say is that so this is basically the power density that we have. So if I take the integral of this power density, so integral of the power density, let's say dP to dV over the volume, then I have also the integral of this one, J2 divided by sigma dV. And of course, in this case, we can the length will not change, so we only take the integral over the surface, but this will be actually equal to 1 over 2 Ri2. So which I can conclude that integral, the surface integral of J2 over sigma is equal to, if the current is 1 amp, so let's say current is 1 amp here, this would be 1, so this would be basically the R AC per meter, ohm per meter. So I can actually use this integral to calculate the RAC if I want. So integral, surface integral of J2 divided by sigma, that gives me RAC. So I should actually write it opposite way. So maybe I should write it like this with red. So RAC ohm per meter in this 2D case is equal to surface integral J2 divided by sigma ds. All right. So what we can do, we can actually do the same thing here. So I right click on derived value. I click on integration, surface integral, and then we select this whole surface. But what do we want to integrate? We want to integrate the current density, normal current density power 2. So we come here, electric current, norm of current density, but I actually want to power it 2. Power 2, and should be divided by sigma, which sigma was 5. Should have defined the parameter, 5.86 e power 7, something like this. This gives us the AC resistance per meter, which actually gives us exactly the same value as we obtained before. Now we're going to check this also for the other cases. All right, so we are done now with the frequency, with the DC frequency 0 hertz. Now what I'm going to do, I'm going to change the frequency to 5 kilohertz. Okay, so the frequency is now 5 kilohertz. And we run the simulation. This is the magnetic field distribution. Now, this is the current density distribution. What we can notice is that, let me raise this one. When you plot this current distribution, you have to always pay attention how much difference is between each location, because sometimes COMSOL assign a color range, which these color range might be very tiny. They do not change a lot, but still it gives you a color range, so you must be very careful. So anyway, I click on the center. You can see that current density is 0.3 ampere per square millimeter, but on the corners current density is 0.32 ampere per square millimeter. And of course, if we see the current distribution over that cut line, over this cut line, over this cut line, where is it? Over this one. So we can see that, for example, at the center it's a bit less, in the corners, like near to the edge of the conductor, we have more. And now if I use this our AC calculation directly by COMSOL, we will have 0.00558. So I just want to write it. Okay, first let me check the other integration, whether this one gives me the same result, obviously. So I'm going to write this one. So we can see that the number here is 0.00558, 558 or 558, not 58. 558 ohm per meter. It increased only a little bit. The reason is because this conductor is already very small. The material is copper, so skin depth is large. So at 5 kilohertz, still this one operates nicely. Now let me increase this frequency to 500 kilohertz, so 2 more 0, and we run the simulation again. Alright, so you notice that magnetic field also is expelled from inside because there's no current now in the inner part. We can look at the current density. We see that in the center we have actually 10 power minus 4, 5 10 power minus 4 ampere per square meter, very small value. Near to the edge, however, we have larger current density, 1.78. And if we look at the distribution, okay, so here maybe I can also add this millimeter. This is better. So this is 1.8 ampere per square millimeter, and then in the center it's a small. One thing, very important thing that you want to notice here is that you see that near to the edge of the conductor, the current actually is very large, okay, the current density. Here in the center is small, but something very peculiar, very unintuitive is that in some region of the conductor, the current density is actually opposite direction. So here you see that it's negative. It's if you look at the current surface plot, you notice that here the current is coming, for example, toward us, coming out of the page. This one is almost 0. At this location, we have the negative current density, which is moving backward. So this is very unintuitive. Imagine if the total current of the conductor is coming toward us. At the edge, of course, majority of current will concentrate coming to us, but just a little bit after that, like in this region, the current is flowing backward. This is really, or at least it has phase shift. Phase shifts such that it creates a negative direction. It's very unintuitive, and it's difficult to explain by simple explanation. You are not able to explain this phenomena. But if we solve the Maxwell's equation, we will see in the next video that all of these things can be predicted, and we will obtain the actual equations, how this kind of distribution will look like for this simple case. Okay, finally, let me show you the AC resistance. Okay, so you notice, let me delete the previous one. So you notice that AC resistance in this case is 0.03. And obviously with the other method also we get same result, obviously. 0.0306. So here we have 0.03061 ohm per meter. Was it 16 or what was that? Yeah, 0.03616. So you already noticed that, for example, between this case and this case, there is not pen attention. So you already noticed that between this case and this case, there is not much difference in the resistance, in the AC resistance. The AC resistance in this case is more or less similar to the DC resistance. However, this is the reason is because the skin depth is still it's covering most of these regions. So that's why we use actually all the cross section, even in this case, almost all. But when the frequency goes high, the skin depth decreases, and we are not using the whole cross section properly. So that's why the resistance is 0.03, which is almost 6 times higher than the previous case, than the DC case. Alright, so this is end of the first video. In the next video, we will see how to solve these equations to obtain basically the current distribution for this round wire. Okay, bye.